So today, what was that? So today I'm going to show you, we're going to calculate one other moment of inertia for an object whose moment of inertia is already on that form that you saw, but it'll be a volume, so we'll approach it slightly differently. Same general procedure. Again, this type of integral setup is something that you really want to know. It's one of the more difficult things that we do in AP Physics C when we did center of mass, when we do rotational inertia. And again, I've mentioned this before when we go to charge distributions and electric fields, and then magnetic fields after that. Not so much with magnetic fields, but with electric fields, we see integrals like this pretty often. So let's say I want to take this cylinder. It's a uniform cylinder. But again, we can do non-uniform cylinders just by replacing the volumetric mass density by the function that it will be defined as. So we want to determine the rotational inertia for this uniform cylinder rotated about the y-axis, which is going right down through its middle. Okay. In calculus, where are you guys at right now? AB calculus. Natural log. Okay. So you're not in integrals yet, right? No. Okay. In BC, or if you've already had calculus before, you know about representative rectangles. That's essentially what we do when we do our integrals of just normal functions. You draw a representative rectangle, and then you just take that rectangle, make its width dx, its height is evaluated as is the value of the function at that point, and then you just add up all those areas. So this is essentially a very similar concept. When we have a rod, we just use a representative segment of the rod. With a cylinder, though, it's a little trickier. We need to use a representative element that's the same as we integrate across the entire cylinder. And the easiest way of doing that is to define a representative cylindrical shell. And so I'm going to take a cylindrical shell with an inner and an outer radius. And give me a second to draw this.
That's not infinitesimally small.
It's not infinitesimally small. It's hard to draw that. So, yes, the width of this cylindrical shell will be infinitesimally small. But because I have trouble drawing things like that, I'm going to go ahead and just...
You probably draw the best diagrams out of any teacher I've had.
Oh, shucks. Really?
Yeah, really.
Huh. That's surprising.
Most teachers don't even draw diagrams.
They always preface it with I'm not an artist.
Well, I always preface it with I'm terrible at drawing. Okay, so imagine I have the cylinder and then I have a cylindrical shell. So it's going to be like say I have a cylinder like this that I'm going to divide into a bunch of these guys, right? An infinite number of infinitely thin cylindrical shells. Okay? And so each one of those will have a mass dm, right? Each one of those has a radius which I'll call little r. That's little r. Where big R is the overall radius of the cylinder. But little r will be the radius of our representative cylindrical shell. And that cylindrical shell will have the same vertical height or vertical distance, length, let's call it length, the same length of cylinder. That cylindrical shell will have the same length as the overall cylinder, right, if I've set it up like this. And the reason I pick a cylinder or cylindrical shell is because its dimensions match that of the cylinder, right? If I take one that's right at the center, then I add up all the volumes as I go out, then I end up with, or the rotational inertias as I go out, then they all fit inside the cylinder and they all kind of nicely line up when they're inside of it. Yes, sir?
So if this were like a solid sphere, then would like these segments be like shells?
They'd be spherical shells, yeah. Starting from the center where it's essentially zero size, and then you add as they go out. Yeah. Mm-hmm. Very good. So are we all on board with that? So the thing that you want to think about, well, first of all, before I even go on, we are going to use the equation that we talked about yesterday, the integral of r squared dm. But I need to talk about mass density. I need to indicate that. And even if I didn't, once I write, I want to determine the rotational inertia of this cylinder. It's going to be the integral of r squared dm. All right, well, dm, that's mass, right? I need the mass density equation in order to express dm in terms of something that I can integrate with respect to, right? See what I'm saying? So I go to my mass densities, put those in another color. I'll say my volumetric mass density, the macro, is just going to be mass per unit volume. But I can actually extend this out because the volume of a cylinder we should know, right? So that's going to be total mass divided by what's the volume of a cylinder? Pi r squared L. Yeah. It's like any prism, right? Area of the base times the height. Yeah. So there's my macroscopic mass density, which if you have followed the few times that we've done this, you know that at the end that comes back to simplify our result, right? But we also want to do the micro mass density, and that's just going to be dm dv. dv is not going to be pi r squared L. dv is going to be something different. But we still need an expression for that because we don't know what dv is. So dv, can anyone tell me what the volume of this representative cylindrical shell will be? Oh, I didn't put the, sorry. I forgot to put the width. dr. Right, the width of that guy, the differential width is going to be dr. You guys know why it's dr, right? The distance from here to here is r1. The distance from here to the outside is r2. So the actual width there is going to be r2 minus r1, or delta r. But then we take delta r as it approaches infinitesimally small. Right? That's why it's dr. I remember that confusing me when I was first learning this, and I was too shy to speak up. So does that make sense to you guys?
Yeah.
Okay. So what's dV? What's the volume of that cylindrical shell? In terms of the stuff that I put up here. You know what I could do? I can slice it and then open it up so it's essentially a flat sheet.
Wow. So it'll be
2 pi r dr times L. Or 2, let's say L, well, yeah, 2 pi r. That is the thickness, right? No, that's the circumference, which if we lay it out is just, think of it when you lay it out, when you slice it and lay it out, it's just a rectangular prism, right? One dimension of which is 2 pi r, one dimension of which is L, and then the other dimension, the thickness, would be dr, right? So that's what dV is there. So my new expression, remember this is our micro, even smaller than micro though because infinitesimal. So I can say that that density is going to be dm over 2 pi rl dr. And then I can just multiply both sides by this, and I get the dm equals rho. Let's do 2 pi first. 2 pi times rho. And I'm going to put L first because R is the thing that's going to change, right? R dr. 2 pi rho and L are all constants. But R is the thing that's going to change. As I integrate over this volume, R keeps getting bigger and bigger until it reaches bigger. But 2 typically doesn't change. Pi typically doesn't change. The density is uniform, so it's not going to change. If the density was not uniform, that density right there is where I would put in the function of R, right? The function of radial position. And then the length is the same for all of them. So the only thing that varies there is going to be R. All right, well now I have that expression. And notice I'm not really integrating with respect to x here. I'm integrating with respect to r because r points in all directions and I'm going out from the center, right? So I don't want to say x or y. I want to integrate with respect to r, what's actually on the formula sheet. So with all that, I can then plug that in to my rotational inertia equation, which gives me the integral of r squared times all this junk, 2 pi rho L r dr, which we probably want to rewrite, right? Yeah.
Oh, I'm already messing it up.
So what's constant? I got a 2 pi rho L times the integral of r cubed dr. Did I do that right? Yeah. So again, the actual integral that we do is very simple. Yeah, that's it. It's the setup that can be tricky, right? The steps leading up to that, in my opinion, are far more difficult than doing that actual integral. That actual integral is very, very simple. And again, representative cylindrical shell. As Gianni pointed out, if I wanted to find the rotational inertia of this solid sphere, I would use representative spherical shells. If I want to find the rotational inertia of a rod, then I use representative segments. Each of these things, each of these representative things would have mass dm, right? But then certain volumes, certain lengths, certain stuff like that. Yes, sir.
I just imagine the ancient Greeks trying to read these formulas as words.
Okay. So what's the integral? Oh, what are my limits first of all? 0 to big R, right? I start from the center, and then R gets bigger for each representative, for each cylindrical shell until I reach the outer edge, which has radius R, or big R, the radius of the actual cylinder. So it'll be R to the 4th over 4, evaluated from 0 to big R. Well, that's easy. It's going to be big R to the 4th over 4 minus 0 to the 4th over 4. Times R to the 4th over 4.
It's like on the essays here, and they give you a massive equation. So like, you know, like it like looks really long, complicated, but then they throw a multiply by 0 in there somewhere. It just makes the whole thing like.
Well, you've had calculus problems where you like fill up a half or a full page of work, and then the answer is like 1 or pi or something like that. Yeah. All right, so I'm going to simplify the 2 and the 4 here. So I get that the rotational inertia is going to be pi times rho times L times R to the 4th over 2, which is not the formula that's on your formula sheet, not formula sheet, because this won't be on your formula sheet, but on that table of rotational inertias I gave you. This definitely isn't there.
Well,
Right.
we have to simplify by plugging in the macro into rho.
Yeah. So as Bradley says, I'm going to take this mass density. Since it's uniform, I can just plug that in for rho. And when I do that, I'm going to put that first. So I'll have, because compound fractions make my head hurt. So pi r squared L times everything else here, which was pi L r to the 4th in the numerator and 2 in the denominator. And we get a bunch of cancellations. Pi 2 r's L cancels. L cancels. That means the dimension, this is a cylinder. A pulley is a cylinder.
It's because
A cylinder could be long this way, could be real thin, same expression.
because it has the same rotational, like
If they have the same mass, they'll have the same rotational inertia, regardless of how long.
Like on average, the mass is still going to be distributed the same distance from the center.
What's that?
On average, the mass is going to be distributed the same distance from the center.
Yes. In regard, but yeah.
The length of it.
Now, if you get the same material and have a larger cylinder, then it's going to have a lot more mass, so it's going to have more rotational inertia. But if it had the same mass, yeah.
You know, we're doing like a uniform circular or a uniform cylindrical material.
Right.
Are there elliptical cylinders?
I don't know.
Yeah.
I mean, I'm sure there are.
That just sounds
Probably make tables out of them or something.
it sounds like it just makes everything more difficult.
It does. It doesn't sound like it.
But that's the general. That's the general. Like the solution to the force equation dealing with orbiting bodies. The general solution is an ellipse. But for very specific circumstances, then it's a circle. But the general solution is an ellipse, which Newton figured out again by inventing calculus when he was barely older than you guys. Yeah,
Step it up.
I'm
In the
already
six-
making my own now.
in the 1600s. Well, I'm looking forward to hearing about that.
It's top secret.
Yeah, he didn't even have Google. He didn't. So what's the answer? All I have is mr squared over 2. Or 1/2 mr squared. This is one that you'll probably commit to memory just because you see it so often. Because now this pulley wouldn't work because this pulley has a bunch of empty space in it because it has spokes. But if you just have a cylinder with a small groove cut through the edge, which most pulleys in physics problems are, then this is the rotational inertia for a pulley, or a disc, or a cylinder.
So if you have a compound mass, like with a bunch of like rods and a cylinder, would you just add the rotational inertia?
Yeah.
Okay,
Yeah.
that's what I was.
Mhm.
So like for a wheel.
Yeah, just like net force on a system equals mass of the system times the acceleration. If you have multiple objects within the system, then the net force on the system equals m1 plus m2 plus ... times the acceleration, right? Same thing, if I have the net torque, and we'll talk about Newton's laws for torque towards the end of this week and when we come back, if I'm talking about the net torque on the whole system, that's going to be the rotational inertia of the system times the angular acceleration. Well, the rotational inertia of the whole system is simply the sum of all the individual rotational inertias, right? In the same way.
I feel
And you have problems like that. Like a common problem is you have a hoop, right? A thin hoop, which you have a rotational inertia for on that form, or on that thing I gave you. And it's got spokes, maybe like 5 spokes. If you wanted to, and each one of those spokes is a rod, rotated about its end, right? And then you have a hoop that's rotated about an axis through its center. Well, the rotational inertia for that guy is going to be the rotational inertia of a hoop rotated about its center plus 5 times the rotational inertia of one of those rods rotated about its end. And you would just add all those up for the total rotational inertia for the system. That's a good question. You want to understand it. You definitely want to understand it.
So what if like there were like some ring in the middle of that group that were like stationary relative to the rotating thing? Like if there's like some like frictionless bearings or something, or like I don't know.
Then it wouldn't contribute.
What if like you're in the reference frame of that hoop though? Could you talk about the rotational inertia of the center? Like to this. I don't know if that makes sense.
Okay, so again, I'm not really picturing what you're saying.
Like if you're like from the reference frame of the what would like the outside part, like wouldn't it appear that the scaling center is moving? Like could you like this whole thing about like rotational inertia, like the Earth is rotating obviously, but we don't like when we see rotating objects on the Earth, we don't really talk about adding the Earth's rotational inertia to it.
Right.
Reference frames, but like
Well, if you want to be technical about it, we're constantly accelerating, right?
yeah,
Our acceleration points towards the center of the Earth,
right.
and so we are not a totally inertial reference frame, but
But if
because we move along with the surface of the Earth, regardless of where it is, then we make measurements like this thing. When I said in this, I don't know if I'm really getting at what you're asking, but when I set this thing spinning, oh my gosh, oh, something came off. Oh, when I said this thing's spinning, the rotational inertia of the Earth is pretty much inconsequential to the rotational inertia of this guy in this configuration.
Like one thing that was like imagine you're in outer space or something, like where there's
What do you mean by that?
Like no friction from air or no like
Okay.
stuff like that. They could like never mind. Let's just move. I just like if you're like in the like if you were on that object, like but if you were in the reference frame of that object, wouldn't it appear that the center is rotating it?
Like if it was rotating and you were inside the object?
Yeah.
Like if this thing was rotating like this and you were inside of it?
Yeah.
Yes, it. And so what's your question specifically?
If you were on the outside object, then it appeared the inside one is rotating.
If the inside one is stable.
Are you stuck to it while it's rotating?
Yeah.
And you don't see any rotation? Is that what you're talking about?
Would it appear as though the I mean obviously but like it would appear that like could you still measure rotational inertia of that center object based on your reference frame in the outside object rotating?
That's a good question.
That's outside of school.
That's outside the school. Well, to directly measure a rotational inertia, it's like mass. To directly measure mass, you got to apply a force and measure the angular acceleration. So
Are you thinking like one of those things on the playground that people were too sensitive and removed all of them because
oh yeah, merry-go-rounds.
I mean not necessarily that. I mean I don't think that would be like a type of
Not only that, but someone tied a truck or a rope around one, tied it to their truck, and sped off with it, and the person on it was killed. I think I remember reading that. Yeah.
What I'm trying to say is like we use imaginary forces all the time in this class, like gravity or the centrifugal force.
In this class, gravity is a force. Okay, gravity is not a force once you get to like
We pretend
junior, senior level physics major classes.
we pretend that it's a force though. In order
Yeah.
to-
Which for us is fine.
But like
I know we make jokes about that, but literally, like, unless you're majoring in physics
yeah.
and you're a junior or senior in college, you will not treat gravity as a force.
I mean just like gravity.
But things like centrifugal forces,
Yeah.
which maybe you're thinking of here, definitely do not exist. And so you're in this rotating thing and you feel like you're being pushed against the wall. You feel like there's a force doing that. And you can measure that force, right? You can measure that force by maybe taking an object, putting it, and seeing how much it gets squished, right?
Right, that's what I'm talking about. Like
But that's not a real force.
Exactly.
But the reason that you're measuring that force is because you are in an accelerating reference frame. If you make measurements within an accelerating reference frame, which is called a non-inertial reference frame, then you measure those fictitious forces. I think the easiest one, think about this. An easier one would be you're in your car and you got something hanging from the ceiling, and then when you start accelerating this way, that thing angles back, right?
I get that. Like, but my question is like that stationary object in the center. If you were in the outside object that's rotating, could you measure rotational inertia based on like the imaginary force of that stationary object that appears to be rotating from your own reference?
Now, if an object is just rotating, you can't. You have to apply a torque and measure its resulting angular acceleration in order to measure a moment of inertia. Right? It's like mass. How do you measure mass? Right? Now you can use a balance beam, but that requires torques.
I mean, doesn't it say 1/2 mass times radius squared?
Yeah, this is just to calculate it. Right? This is just whether it's rotating or not. Right? This disc has the same rotational inertia whether it's sitting there at rest like it is or whether it's actually rotating.
I see.
Was that like a super roundabout way of answering your question?
Rotational momentum. Is that
Angular momentum.
angular momentum? What
Yeah.
about that? If you measure
We'll get to that when we come back after the break.
Okay.
All right. Sorry about. I should have probably seen. I don't know. It's been a long week.
Like, could you measure the imaginary angular momentum of that object in the center? That's basically what my question was.
I don't know. I'll think about that. Not sure. All right. So the one thing I want to talk about. I think I need to. So we've done some technical stuff here, but you got to understand at a visceral level or just a conceptual level what rotational inertia is all about, and it's all about the distribution of mass, right? You have an object, these two objects here have essentially the same mass, they're slightly different, but they're manufactured to have the same mass. And so if I push on one of them with a certain force, it'll experience a certain acceleration. If I take the other one and put it at a different orientation than the first and push on it with the same force, it has the same acceleration as long as I don't rotate it, right? If it starts rotating, then that means I've also applied a torque. But if I just push on it in just the right way so this guy accelerates that way, and I push on this guy like that so he accelerates that way, with the same force, these two equal masses will experience the same acceleration. That's why Newton's laws for translational motion is a lot easier than Newton's laws for rotational motion, because Newton's laws for rotational motion, it's not just the mass of the object. And remember that for a point mass, the general equation that we use to determine rotational inertia is mr squared. So not only is it not just the mass, but the mass is not nearly as important as the distribution of the mass, which is represented by r. Right? R tells us how far from the axis of rotation the mass actually is. And it could be a single mass, or it could just be how that mass gets distributed. So when I have two equal mass objects like this hoop and this regulation size hockey puck, these two guys have the same dimensions, they're the same radius, they have the same mass, yet one of them has a much higher rotational inertia. Which one do you think has the higher rotational inertia? The one in my right hand? Left hand?
My right hand on your body is that one.
This one has the higher rotational inertia. Because, think about this. Think about all the mass, all the little tiny DMs that are inside of this hockey puck. The ones that are closer in have smaller R values, right? So as I move them out, the R values start to go up. So if these are the same mass, then all the mass that would be in the middle in the hockey puck with really tiny R values, all that mass now gets a pretty large R value. That R then gets squared for each one of those little pieces of mass. And so the total rotational inertia for this guy is actually quite a bit larger than the rotational inertia for this guy. Okay. The same thing applies to, right, if Gianni wants to get in a fight and I hit him with this, right, or he hits me with this, maybe I'll say that, it's not going to hurt that much, right? It'll sting. It'll sting bad, but it's not going to cause any damage, right? But if I take that mass and bring it out here, like that's pretty heavy. That's a good 300 grams. And if he hits me, if he gets this thing if he gets this thing rotating at the same speed, this is going to cause a whole lot more damage, right? And that's because there's a lot more rotational inertia in this configuration than there is in this. For the same reason that there's a lot more rotational inertia in this configuration than there is in this, right?
That's why a hammer is so,
What's that?
a hammer.
Yeah.
Because the weight is distributed.
The weight is distributed towards the end, and the longer the handle on a hammer, the easier, the better you need to be at it, but the more likely you are to get it driven into the wood. But here, just looking at this, instead of having, like, essentially the mass gets distributed on both sides, but then if I take all the mass, I still have essentially the first half of the mass is distributed the same, but I've taken that other half and I put it even farther out. And because the distribution of the mass, which is described by the R value in the rotational inertia equation, I get so much more rotational inertia. And that's why it goes from 1/12 ml squared to 1/3 ml squared. It's actually 4 times more, right? Which means if I hit you like this, it'll hurt you 4 times more than if I hit you like that.
Hurt you 4 times harder.
4 times, 4 times worser? 4 times worser. I'll hit you 4 times harder. How about that? Okay. So it's all about the distribution of the mass. And this is why the medieval weapon, like if I was in medieval times and I had the choice between getting stabbed or getting hit by a big mace, I'd much rather get stabbed. Because that mace, devastating, right? You can get stabbed and if it heals and if they miss the organs, then you'd be okay. But man, getting hit by a mace, crushing bones and stuff, oh, that'd be terrible. So, mace is devastating weapons because they take all the mass in it and they put it out towards the end to increase that rotational inertia. And as we'll learn whenever we talk about net torque, well, you got to apply more torque to get that moving, but then whatever you hit has got to apply a lot more torque to get it to stop moving, right? And so whatever you hit has to stop that rotation. And Newton's third law says whatever force it exerts on the mace to stop it from rotating gets exerted back on it, right? So keep that in mind, Gianni, because I have it. You don't have it. I have it. These aren't weapons. These are physics demonstrations. Yeah.
They also apparently, like according to the government, like a laptop is a weapon.
Yeah. And also it has to do with like trying to balance this, like this, pretty impossible. But you distribute the mass differently, and it becomes whoop.
Still pretty impossible.
It becomes it's much easier. This is actually possible. Much more possible. Right? All right. It's both simultaneously. All right, that's my spiel for today. Use the rest of the day to get started on your new quest assignment. Remember, it's the distribution of the mass. Equal massed objects. The more, if you have equal mass objects, the more mass distributed farther away, the higher the rotational inertia. Cool.